going to look at an application of implicit differentiation. So the application I think is actually easier than doing the implicit itself because we're going to talk about some real life problems. We're going to take the derivative of a price and say a supply or a demand with respect to time. So we have money that's changing with respect to time, so the price is going up or down, and then the demand, how much people want. They see the price goes up and their demand goes down. So we have two things changing with respect to time, and none of the original variables were time. So we're going to see when we take the derivative of x with respect to time, we'll have a dx dt, and derivative of price is going to be dp dt. So it's nice because we get some concrete numbers and everything has a d something dt. So there's some consistency here. So if a manufacturer of disk drives is willing to make X thousand flash drives. So I'm going to bring this up here. X thousand flash drives. So I'm given a unit on this. And X is in thousands. So if X is demanded is 5, X equals 5. That doesn't mean just 5 flash drives that they're demanding. It means 5,000. And then these are in stores for a wholesale price P, which is dollars per drive. It is known that the relationship of x and p is given by x squared minus 3xp plus p squared equals 5. And we want to figure out how fast is the supply of drives changing when the price per drive is $11. So my price is 11. The quantity supplied is 4,000 drives. So x equals 4 because that's already in thousands. And the wholesale price per drive is increasing. We're trying to raise our price at a rate of 10 cents per week. So we're going to do the same setup and it'll help us solve all these problems. So my first variable I'm given is x thousand drives. So I'm just going to write that out and we'll do this every time. So we have x thousand drives. The next variable I'm given is P. P is in dollars per drive. That's how much we're charging for each of them. And the other thing that I know is my time here is in weeks because it says we are increasing our price by 10 cents each week. So T, we're not changing it every month or every year, we're changing it every week. Trying to see how that affects our supply that we have in stock. So the X value that I'm currently at, well, the quantity supplied is 4,000, and this unit on X is already in thousands. So X equals just 4, because the unit on that is 1,000 drives. And we're going to see how that's changing with respect to time. So every time I write X, I'm going to write the units on it, and then I'm always going to have a dx dt. How is the supply changing with respect to time? And if I don't know that yet, I'm just going to move on to P. I'm filling what I know. So I have P, a unit on it, and then under there I'd write P, and then we're also going to take the derivative of that. We're going to find the rate of change with respect to time. So we have the same type of setup for all these problems. X, P, dx dt, dp dt, and then at the top we just have our units. So P, am I given the price that the drives are at already? Yes, the price per drive is $11. So I'm currently at $11. Any other information I have here? So $11, the supplied amount is 4,000, so we already put that X equals 4. The price per drive is increasing. So I'm given a rate of change, and it's the price per drive. So I want to think, am I given dx dt, how the thousands of drives are changing with respect to time, or am I given how the price is changing with respect to time, dp dt? So this price is increasing by 10 cents. This must be dp dt. And dp dt should be the units on P, which is in dollars, and then the units on T, which is weeks. And how we're changing it in dollars per week is by 10 cents, so that's $0.1 per week. And since we're increasing our price, this derivative should be positive. If I was decreasing the price by 10 cents per week, I would do that as a negative $0.1 per week. But instead, we're increasing it. and I'm asked how fast is the supply of drives changing. So I'm asked to solve for this rate of change. So your final answer, you're always solving for one of your derivatives. So here I'm solving for dx dt, so I'm going to figure out how many thousand drives, that's my x unit, so 1,000 drives per week. How much is my supply changing as my price is increasing by 10 cents? How many thousand drives is it changing by? So this is what I should be solving for. Related rates, these problems here, we're always solving for one of our derivatives. So now I need to take the derivative of the actual function I'm given above. So my function that I'm given is, these are related by x squared minus 3xp plus p squared equals 5. So I don't want to plug in right here. I want to plug into the rate of change. So I need to take the derivative of this. So I rewrote this just to take the derivative of it, because that's what we're going to use. So my derivative of x squared is 2x, and I'm taking the derivative with respect to time. So I'm going to need a 2x dx dt. Here I have a product rule. So I have the product negative 3x times p. So I'm going to use my product rule here with respect to time. So derivative of negative 3x is negative 3 dx dt. Take the derivative of x with respect to time. Derivative of the first, negative 3x, times my second is p. So derivative of the first times the second, plus always for product, the derivative of the second. Derivative of 1p is just 1. I took the derivative of p with respect to time, so I need a dp dt. So derivative of the second is what I just did there, times the original first, negative 3x, equals the derivative of 5 is just 0. So it's a tough derivative just because I had the product rule, but it's nice. Everything gets a d something dt. I don't have to think about it too hard. Take the derivative of x, put a dx dt. So now I get to plug everything in. It's nice we have concrete numbers this time. We should know a number for everything besides dx dt, what we're trying to solve for. So I have 2 times the x value, which x is 4. That's our current demand. And I have that multiplied by dx dt, what I'm trying to solve for. How is the supply changing, rather, not demand. Minus 3 times dx dt. I usually like to write these at the end, but I'll put that there. Times p, my current price is $11. Plus 1 times dp dt. The price is changing by 0.1 because it's increasing by 10 cents. Times a negative 3 times my current x value, which is 4, equals 0. So lots of numbers to keep straight here and plug in. And actually, we forgot to take the derivative of p squared. Let me pop it up here. We need to add on to our derivative as if it wasn't long enough. Before we take the derivative of 5, we're going to backtrack. The derivative of p squared is plus 2p dp dt. Felt like I was missing something. Equals 0. So we have plus 2 times my price is 11 times dp dt. The price is changing by 0.1 equals 0. So I've kind of intentionally made a mistake. It's not really a mistake. I want you to realize that these derivatives are long, and don't forget to take the derivative of something. So sometimes you'll forget the simple part like p squared, and the other common mistake I see, which I'm not going to intentionally make it, is forgetting the derivative of 5 is 0. So I don't want to leave that 5. This is already a lot of work. I'm going to make sure I have that equals 0 on the right. So now that I plugged in, I just want to figure out what these numbers are. So I have 2 times 4 is 8 dx dt's. Then I have a negative 3 times dx dt times 11. So negative 3 times 11 is negative 33 dx dt. And then I would want to just combine all these constants. So 1 times 0.1 times negative 3 times 4 is going to be a negative 1.2 when I plug that into my calculator. And then I have 2 times 11 times 0.1 is going to be plus 2.2 equals 0. So we can combine what we have here. We have 8 dx dt and we subtract 33. So we're at negative 25 dx dt. And then we have negative 1.2 plus 2.2, which is just 1, equals 0. So now I've plugged in, combined like terms, and now I'm going to get dx dt by itself by subtracting 1. Negative 25 dx dt equals negative 1. And then lastly, I'm going to divide both sides by negative 25. That way I get dx dt by itself. So, if I plug it on my calculator, dx dt is going to be negative 1 over negative 25, which ends up being a positive 0.04. And I'm just going to throw my units on here. It's 1,000 drives per week. That's how much that supply is changing by. So I want to be able to interpret this. So first step to interpreting this, I'm just going to change that 0.04 by multiplying by 1,000 and seeing how many drives that really is, because 0.04 of 1,000 drives doesn't help me too much. But if I multiply by 1,000, that is 40 drives per week. Just figuring out how many that is. So my conclusion is the demand is decreasing or increasing here. I want to say that as part of my conclusion. Well, I have a positive derivative here, so my demand must be increasing. Or in this case, we're talking about supply. So the supply, that's my original function here, x is the supply, is increasing by 40 drives per week as the price goes up by 10 cents per week. I'd write that full sentence out if we wanted to. The main thing we want to pick up out of this is the supply is increasing because they have a positive derivative. It's increasing by 40 drives per week, which makes sense. As we increase our price, we'll have more supply kind of left over.